My name is Ruslan Nigmatullin. I'm software engineer at runtime team at Dropbox. And today we will talk about Susanin. It is that service discovery system at Dropbox, named after a historical Russian character famous for his logistic skills. So what makes building service discovery at Dropbox especially challenging? We have pretty good scale. We have multiple data centers with few tens of thousands of hosts on in every one of them. We have tens of millions of clients, which in average generate up to tens of thousands of state changes per second in service discovery, which usually means registrations or deregistrations or some hosts going away. So at Dropbox, we've decided to build, few words about service discovery. In modern world, service discovery is a very dynamic problem. Hosts are all constantly going away. We spawn new hosts to extend our capacity. We deploy services all the time, which leads potentially them starting on different hosts or using different ports. So we need to propagate all this information to all of their clients in timely fashion. Also, it's important to understand that service discovery is an eventually consistent problem. It's more important to provide some information to clients about how to resolve the backends, where to send traffic, compared to not giving any information at all. Even stale information would be generally useful and allows your site to not go down. In order for that, we actually highly prefer high availability compared to consistency, and are constantly making such trade-off. Therefore, at Dropbox, we've decided to build service discovery based on Zookeeper for multiple reasons. First of all, we already had, by that time, some operational expertise running Zookeeper on our scale using tens of thousands of clients. And based on that, we figured out how to operate it correctly, how to build a proper automation around it to not bring it down during regular nodes replacements or some other more drastic operations like redeploying binary with new version. As well as we figured out how to actually not use Zookeeper, which is probably more important, which generally allows to build safe guardrails to, if not prevent the abuse of Zookeeper, but at least be able to detect these misbehaving users early enough. Also, starting from Zookeeper 3.5, it actually supports read-only mode, which allows us to make a choice in the trade-off between consistency and availability towards the latter. So let's talk about how to make service discovery actually scale. So one of the common approaches would be to use Zookeeper in, let's say, naive way. So let's assume we have multiple hosts. Host X hosts have several instances of service A, and host Y wants to discover these instances and figure out that it wants to send traffic to them. Usually, what implementations of service discovery do, they make each service connect to Zookeeper directly, and for every registered instance, make exactly one file in the Zookeeper under the directory for this service. It is very simple code. Second process on the same host or on any other host connects to Zookeeper one more time and creates file there as well. These files are usually marked as ephemeral, so that if host goes down or process crashes, it's automatically removed from service discovery in timely fashion, which depends on your configuration of session timeouts. Now, clients want to find these services and find these backends. So for that, it makes a full scan of the directory, issue and children call, and after that, iterates over all the childs and reads them one by one. And after that, parses the received data and therefore is able to get the list of addresses. Now, this approach is fairly simple. Without error detection, or error coverage is just a few lines of code on both client and server side, assuming you have decent Zookeeper library. But there are a few issues. First of all, load to Zookeeper, in that case, scales up with number of your clients, both clients which want to watch your data and clients which want to register in service discovery. This also, as all clients are connected to Zookeeper directly and are receiving notifications about any changes at exactly the same time, this solution is also susceptible to thundering heart problem, as all of them will also, if uncoordinated, will try to read this data from Zookeeper at the same time, effectively causing spikes of the load. Also, as all clients are connected to Zookeeper directly using stateful sessions, in case of Zookeeper being slowed down, it actually starts, under heavy load, it may slow down, which may cause it to expire some sessions, effectively causing clients to reconnect. And in that case, clients will reconnect and issue more writes to Zookeeper and more reads, causing it to go even slower, which will cause more clients to go away because of expiration, which effectively creates a positive feedback loop, which may bring your Zookeeper down or some other backend and never recover, potentially. And due to mostly the same reasons, this setup is also susceptible to various network outages, like partitioning or just network flakes. And in case because it may lead to massive session invalidation, which can go again into a positive feedback loop. So let's think, what can we do to scale it? So sessions, clients connecting to Zookeeper directly use stateful sessions, which cause writes on every connection and disconnection. And Zookeeper can handle only a certain amount of writes per second. Using spinning disk setups, it's usually up to 15,000 writes per second. And another problem is positive feedback loop. So how to tangle it? So let's go back to our previous setup. All clients are connected to Zookeeper directly. So what can be done? One of the approaches is to create a local daemon on every host and tell that this is their only process which is allowed to be connected to Zookeeper directly, effectively multiplexing all reads and write requests through it. In that case, all the processes and all your clients use very thin API. As daemon is the only implementation, the only user of Zookeeper, everyone else can use some high-level RPC like gRPC or Thrift. So it allows us to reduce number of connections quite severely, especially if you're running large boxes with especially a huge amount of processes on them. Also, it allows us to introduce read cache on all of the instances, effectively allowing us to multiplex reads and reduce read load to Zookeeper. But there are still few issues left. We still have positive feedback loop. Write load to Zookeeper still scales with number of instances registered in it, as every instance have to issue an individual write. And for read, we still have to do the full scan of the service directory and reread all entries, which can be problematic if your setup of tens of thousands of instances restarts at roughly the same time. So maybe we can rethink how can we use Zookeeper or other backend in the first place. Maybe the constraint of having the same register and resolve path is too aggressive. So how can we optimize it? On write path, probably the most optimal way, as we already have a daemon, is to issue exactly one write to Zookeeper with the whole state. This state would contain the snapshot of information, which is generally a mapping of all services registered on that host to their associated addresses. Now, the problem is, previously we used ephemeral files to detect if host goes away? Can we use it here? Unfortunately, the answer is no. Ephemeral files are owned by individual process and by individual session. And the session is usually attached to individual process. If we restart the process, which happens in the case of the global deployment of the local daemon, we effectively have to revalidate all the sessions associated with this daemon. And therefore, we are losing an ability to control this file created by previous instance. So, which means that health should be explicitly defined by some other means. Another issue that if we, for example, create multiple data files, we have no way to determine which one of them is the correct one. By having exactly one data file and outsourcing health to some other place, we solve this problem. So it leads to making daemon create two files, one with actual data, the latest snapshot, and the health indicator of the health of the system. Now, also, like, as this is the single file, we are able to aggressively coalesce it, and even after prolonged periods of inactivity, we can make exactly one write to Zookeeper, and in order to keep up and write the latest state. So even if Zookeeper slows down, we can still reduce rate of updates and keep up. Now, on the read path, we probably want to read also exactly one file, indexed by service name. In that case, we also get roughly the same property. We are able to coalesce reads, and by that, we can, again, always keep up. Even if Zookeeper slows down, we can sleep a bit more, still make a single read to Zookeeper, and fully initialize ourselves. Now the problem. We have two different representations of data. How do we convert one to another? Our approach was, which we may recommend to you, is to introduce a separate control plane. In our case, it's called aggregator. This allows us to, this aggregator is the single instance somewhere in the cloud, which connects to the same Zookeeper, operates on top of it, and reads all data indexed by host, and converts this data to per service model. For achieving high availability, we are using literal action to maintain multiple standby copies of this aggregator, and if one of them goes down, we use another one. This gives us clean separation of control and data planes, which unblocks our ability to have slightly different design options. Also, as all writes and reads are performing snapshot-based operations, it's actually more or less constant runtime complexity. It does not depend anymore on the number of instances of your service. It does not depend on number of your clients on the given host. So load only scales up with number of hosts, and it does not scale with neither number of clients or rate of updates in the system, as we always are able to keep up due to heavily coalescing of all requests to Zookeeper. Now, at this point, we've built some scalable system. Now the question is how to use it. We probably want some relatively simple API, so that software engineers, while trying to use it, will not have an ability to bring your system down, and will not have any way to abuse it. For these purposes, we can go back to DNS, which works pretty well for the last several decades, and provides roughly similar API. So we assume that every service is actually a path, and if you want to register in service discovery, you just go to local daemon through very simple RPC. Tell, here is my service name, here is port, I'm listening, and are able to accept traffic for the given service. On client side, it's also very thin client, which, given the service name, can go to local daemon and get list of addresses. To support dynamic nature of the cloud, we're also providing watcher-based API so that you're able to dynamically notice any changes and adapt to them in real time. Like if you want to scale your service, spawn hundreds more of instances, and load is distributed automatically among them. But at Dropbox, we technically do not use service discovery directly. It's heavily integrated in gRPC. So whenever you create a server or client, it transparently uses service discovery under the hood. And a few more words about our RPC stack. Our RPC stack is named Courier, and it is heavily integrated with our service discovery, so that whenever you use this RPC stack, you are using service, like, you don't have to think about where your instances are running. Your clients will be able to automatically discover servers and distribute load to them. It's also is based on mutual TLS to support authentication, which allows us to actually aggressively misroute traffic and use stale data, and like misroute clients, but they still will send traffic only to the desired endpoints, which is quite safe property. We've also built various circuit breakers, like rate limiters and LIFO queues, to prevent overload and be able to gracefully degrade under the heavy load. And it's also heavily integrated with metrics and tracing to give mostly like visibility for services, mostly for free. More information is available in our tech blog. I will share these slides. Like these slides will be available later for the download on the USENIX. So, okay, let's assume we've built this system. Let's assume it's relatively easy to use. Now, how do we know that it actually does work? So let's talk a bit about monitoring and operations. So we track few metrics on per data center basis, like few words like due to the fact that we have multiple data centers, we run multiple isolated instances of Susanin in different one of them. And in case if we want more isolation, we actually occasionally run multiple different service discovery setups per data center to isolate different potentially abusive users. So how do we define key metrics for service discovery? First one of them is write availability. It technically means that we are able to register in service discovery, and the change is observed by all clients. And for Zookeeper, write availability actually means that we have majority of the quorum. As long as we have it, we can have only short periods of potential inactivity. Next is read availability, which is defined as we are able to read some potentially stale data from service discovery. Again, as system is heavily dependent on Zookeeper, it means that Zookeeper has at least one node out of quorum out of 5 alive, due to the fact that we are able to use read-only mode. And also, even that is over-aggressive. Due to the local caching on every daemon, we're actually able to serve some data even after Zookeeper is fully down for some periods of time, if we do not try to access any new data. And the last property we are looking for is propagation latency, which is how much time does it take for any state in the service discovery, and for any state change in service discovery to be propagated, to the last client. Now, we've defined how, if system works or not, but how can we theoretically verify it? For that, we use different techniques. One of them is Blackbox monitoring. So a few words about black box monitoring. Like black box, like if we assume that system is black, if we treat the system as black box, we can only observe its behavior through some high-level API. Everything under the hood we consider inaccessible, and we think that system potentially tries to prevent us from checking if it's alive or not. So, but it also allows us to answer the question, does the system do what user actually expects it to do? In case of service discovery, we have few processes in the fleet which constantly register in service discovery, track the latency until this client can observe change made by it. So it goes through the whole pipeline of making requests to the daemon, writing it to Zookeeper, read it by aggregator, and return back to per service-based index, and actually be able to fetch by daemon again. And this allows us to measure latency, what time does it take for this propagation to actually be gone through the system, as well as availability. If we observe the change within our SLA for latency, we treat it as success. Otherwise, we treat it as failure. And we have similar setup for Zookeepers in order to be able to determine if it is Zookeeper down or high-level service discovery is down. For Zookeeper, we use ephemeral writes and reads so that if health checker process goes away, we automatically clean up all data and don't leave any garbage. As we've built system ourselves, we are actually able to use Whitebox monitoring as well and peek into internal state of the system using various introspection APIs. Among other cases, it allows us to read the state of all the local daemons and determine if any daemon is outlier and for some reason does not observe the global changes, and allows us to actually detect these issues much earlier than users do. Another is, as we have two different views of the data, we are actually able to compare them and determine if they are consistent to each other or not, using some different code path to even be able to find bugs in the aggregator or related logic. This actually allowed us to find quite a few bugs. One of them was a bug in the replication logic of Zookeeper itself, in the cases when it is forcefully killed and observer, and follower has to read all data from leader. And another bug was in our leader election implementation, because it's hard to make it right on first attempt under certain edge cases. Now, as we have SLA, we can also use the error budget in order to determine, in order to additionally stress out our system and have additional verification that system is resilient to more massive outages. We do various checks like forcefully kill Zookeeper or restart it gracefully, kill aggregators, check that system is still checks end-to-end, as well as we forcefully shut down network on the leader to determine abnormal paths. And as a bonus, we also shut down majority of Zookeeper quorums to verify that read mode still works. And we are able to handle even massive outages without bringing our service down. This also allows us to find a few extra bugs, including lack of timeouts under certain conditions in Zookeeper, when you kill leader and quorum just stacks forever. Stuff happens. So what I hope we would have been able to learn from this discussion. First of all, ability to coalesce all operations to Zookeeper allows us to eliminate positive feedback loops and scale even further. And runtime complexity analysis was actually a heavy part of the determining what would be viable approaches for building service discovery. In our case, it allows us to move into the direction of of reducing number of operations to the upper bound per second. So it does not depend on actual load anymore. And separation of data, which is like daemon planes and control plane, which is aggregator, allows us to have more design choices compared to situations when clients are the only cooperative things in the service discovery. And we've also used verifiable consistency as an end-to-end test to verify that system actually works in production as a source of truth, more or less. As we have service discovery, like reliable service discovery, we actually are able to build on top of it. And currently we are working on more sophisticated ways of doing cross-data center load balancing, as well as more sophisticated load balancing within data center to detect and mitigate outliers, improve overall latency, and utilization of the fleet. If you are interested working on these similar problems, we are hiring. And thank you for your attention.